Welcome to Microcoder videos and to this supplemental video on the Microhard series that we've been running lately. In this video, we're going to be discussing a little bit more about binary numbers and in particular one's complement versus two's complement. Computers and digital circuits use binary logic to perform their operations, including representation of numbers. This means that numbers are represented using ones and zeros instead of the more familiar 10 digits of the decimal system. For example, 10 in binary represents a number equal to the number 2 in decimal. Complements are used to distinguish between positive and negative numbers and to simplify subtraction. And in this study, we're going to be looking at complements and how they're used in digital circuitry as well as in computer logic. And there are two major types of complements, one's complement and two's complements. And we'll be looking at the difference between those two in this brief video. Binary number conversions are necessary in order to convert between the binary numbers as they're represented in computers and the decimal numbers that we normally use. For example, one way of looking at binary numbers is as all positive integers. In that sense, if you look at the binary number, no matter what you're looking at it as an integer starting from 0 up to the largest number that the binary number can represent. For example, in 4-bit binary numbers, 0000 is equal to 0, and 0001 is equal to 1. 1000 is equal to 8 because 2 to the third power is 8, and this represents 2 in the third power column. And then 1111 is equal to 15 by combining 8, 4, 2, and 1, and adding those up gets you to 15. The largest number that you can have in a positive 4-bit number is 1111, or 2 to the 4th power minus 1. 2 to the 4th power, of course, is 16. You subtract 1 from that to give you 15, and that's the largest number you can represent in 4 bits. But what if you want to represent negative numbers too? Well, if you want to represent negative numbers, you have to use some other convention so that at least a part of the binary numbers represent negative and a part of them represent positive. And by convention, the first digit in a negative binary number is the sign bit. For example, 1111 would be a negative number if you're going to use that convention. But how would you interpret the remaining digits? Would this be equal to 1, or is it equal to something else? Well, we're going to cover that in a few moments when we get to it on another slide. Let's look first of all at the ones complement. The ones complement is the simplest form of complement. To create the ones complement of a binary number, you flip all of the ones of a number to 0 and all of the zeros to ones. This works for both positive numbers and negative numbers. For example, the 8-bit number 0001 0000 is flipped to 1110 1111, And you can do it the other direction. If you have the number 1110, 1111, which is a negative number in one's complement, that would flip to 0001, 0000. In this example, the left-hand number represents the decimal number 16, and the right-hand number represents the number negative 16. This one is in the 2 to the 4th power column, and 2 to the 4th power is 16. Similarly, but perhaps confusingly, this 0 is in the 2 to the 4th power column, and it represents the number negative 16 in this case because it starts with a 1. To convert a negative binary number to decimal, in other words, if you want to find out what is this value in decimal notation, you have to invert the number to its, well, the first thing you do is write down the minus sign, and then you have to invert the number to its ones complement and write its value down as the negative number's absolute value. So in this case, where you have the number 1110, 1111, you have to invert the numbers to 0001, 0000, write down the negative, and then take the decimal number that this represents. And the decimal number, of course, would be 16. So you have a minus 16 is the value for this number over here on the right. The 2's complement is slightly more complicated than the 1's complement, but it has a number of advantages, and it's generally the preferred method for representing negative numbers in digital logic and in computers. Creating a 2's complement starts the same as the 1's complement by inverting all of the 1's and the 0's of a number, but then you need to add 1 to the result. And a couple of examples here. 0001, 0000, which is the number 16 as we saw before, is inverted to be 1110, 1111. And then you add 1 to that, 1110, 1111 plus 1, and through normal addition you get 11100000. And this number in 2's complement represents the number 216. You see the difference in this number and the previous number that we looked at on the previous slide. This number ends with 3 zeros, whereas before the number ended with 3 ones. Now, to go from a negative to a positive number, you do the same thing. You take, in this number, this negative number, 11110000, you take the inversion of that, 00001111, then add 1 to that, and that brings us to this number, 0001, 0000, and that is the number 16. So you write a minus down, and then take the numbers 2's complement and write down the result after converting it to decimal as the absolute value for the negative number. Logic gates for the 1's complement and the 2's complement are fairly simple. The 1's complement is very simple. You just take the number on the left hand, the input here, and run it through the NOT operator. And this is an 8-bit NOT operator, an 8-bit input, and 8-bit output. And you can, for example, give this number the 00001,000 positive number and run it through here, and that gives you the ones complement, 111101111. And the twos complement is just a little bit more complicated. You take the 8-bit number input. We give this the same number input here in our example. At this point in the circuitry, you get this number here, the same number that comes out of the ones complement. But then with an adder, you add 1 to that number and you get this result, 11111,000, which is equal to the which is equal in twos complement to -8. This is +8. This is -8 in ones complement, and this is -8 in twos complement. Well, why do we have two different systems? Why not just one system and just everybody uses ones complement? Well, the reason for that is that twos complement solves a few problems that are created with the ones complement system. I'll illustrate that first by looking at the process of counting, in this case counting down from a number until we go negative. In ones complement, for example, starting with the number 0011, which is positive, that equals the decimal number 3. And as we subtract 1 in each row here, we go down closer to 0. 0010 is 2, 0001 is 1, and then 0000 is 0. If you subtract 0001 from 0000, the next number in line, due to an overflow, is 1111. But in ones complement, that's also a negative. The next number down from 1111 is what did I say? This was also a negative. This is also a 0. This is 0. This is also 0 in ones complement. The next number down is 1110. That is -1. And then 1101 is -2, and 1100 is -3. So you can see a problem here already in that ones complement. We have two different representations for the number 0, and that could give you some problems with comparison and so on. If you wanted to subtract and figure out is this the result of 0 or what, you'd have to do two different tests in order to determine, or you may have to do two different tests in order to determine if that number is 0. On the other hand, twos complement doesn't have that problem. With twos complement, 0011 is 3, just like in the ones complement system. 0010 is 2, 0001 is 1, and 0000 is 0. But 1111, instead of equaling 0 again, 1111 represents the number -1 in the twos complement system. 1110 represents -2, 1101 represents -3, and 1100 represents -4. And so the order of progression going down occurs naturally under the twos complement system. There are some other interesting differences between that. other than the representation of 0 as we just looked at. For n bits under the ones complement system, for n bits, the lowest number in the system is 2 to the nth power minus 1 multiplied by -1 to make it negative. And for a 4-bit number, for example, the lowest number here is 2 to the 3rd power minus 1 multiplied by -1. And 2 to the 3rd power is 8, minus 1 is 7. Multiply that by -1 to give you the negative number, and that gives you -7. So the lowest number for a 4-bit ones complement number is -7. And the largest number is 2 to the nth power minus 1 minus 1. This is a positive number, and it's equal to the number 7. So for a 4-bit number under the ones complement system, the lowest number is -7, and the largest number is +7. You see the reason for that is in that the first digit in both the positive and the negative represents the sign. It doesn't represent a number, it represents the sign. And so this is a sign, and then this is a number, a number, a number. For a positive number, you can the largest positive number is 0, 1, 1, 1. That's 7. And the largest negative number is 1, 0, 0, and 0. That's -7. And this complicates arithmetic operations because of something called the addition, because of the addition of the end around carry bit. And we'll look at that in just a moment, and that it'll make a little bit more sense when we look at some examples. The two's complement, on the other hand, as we saw, has only one representation for 0. And that means we get an extra number place, another place for to use as a number. And that means that the numbers are a little bit different here when we calculate the lowest number and the highest number. The lowest number for two's complement system is 2n minus 1 times the -1. In this case, with a 4-bit number, the lowest number is -8. Whereas in the 1-bit system, the lowest number is -7. And the largest number is the same in both. The largest number in a 4-bit system would be 7 here for two's complement, as well as the 1 complement. And the reason is the number 1, 1, 1, 1 now is equal, in the two's complement system, is equal to 1. And that means you have one extra number to use in the system. It uses the same arithmetic logic as a positive integer, but positive integer logic uses, because it does not require the end around carry bit. And finally, let's look at the end around carry bit so that this is understood. And this may be the main reason why the two's complement system is preferred over the one's complement system. Let's give an example of some addition. All of these numbers are interpretations of what this first number is. It's under different systems. In this column, we're interpreting it based upon the one's complement system. In this column, we're interpreting it based upon the two's complement system. And in this column, we're interpreting it based upon the positive integer system, where all the numbers represent positive integers, regardless of the first bit, the value of the first bit. In binary, this number, 1, 1, 0, 1, in the ones complement system represents the number -2. And 1, 0, 1, 1 in ones complement represents the number 4. If you do normal binary arithmetic with these two numbers, you get this result. It's a 1, 0, 0, 0 in 4-bit. We're talking about 4-bit arithmetic here. The result would be 1, 0, 0, 0 with a carry bit. And the carry bit you have to take into account in the ones complement system, and bring it bring it down and add it back in to the ones column to get the real value for the ones complement system. 1, 0, 0, 0 plus 1 is 1, 0, 0, 1. And so this 1, 1, 0, 1 in the twos complement system equals -2. The next one equals -4. And 1, 1, 0, 0, 0 or 1, 0, 0, 0, either one of those numbers is equal to -7 under the ones complement system, and that's obviously the wrong number. To get the right number, you have to do that end around carry bit. So after the end around carry bit, the ones complement number is equal to -6, that's the correct answer to this problem. The twos complement system doesn't have that problem. This number 1101 under the twos complement system equals -3, and 1011 is equal to -5, and that's the only reason for that is because the different way that we interpret these numbers under the twos complement system. So -3 plus a -5 is equal to -8, and that's what this number represents in the twos complement system. 1, 0, 0, 0 represents the number -8 in the twos complement system. You don't have to worry about the carry operation that takes place here, because all this is doing is duplicating the sign bit. And conceptually, all the digits on the left out to infinity are equal to the number 1, because you repeat that sign over and over and over again. If you add digits to the binary number, in order to keep it equal to -8, you have to continue to add ones on the left-hand side. So that's just equal to a -8. Or positive integers, this is a little bit interesting case, maybe a little bit confusing. This number 1101 as a positive integer is equal to 13. Where did you get 13? Well, you take 8, add that to 4, which gives you 12, and add 1 to that, that gives you 13. And then 11, take 8 plus 2 is 10, plus 1 is 11. So it's 13 and 11. And if you add 13 and 11, that will give you 24. If you look at this 5-digit number here, that 5-digit number, if you interpret this as, if you look at that as a 5-digit number, that 5-digit number is 24. This is 16. This would be equal to 16 plus 8, and that's 24. In 4-bit logic, it would be an overflow condition, but otherwise, it's just a regular binary arithmetic. So there's no difference between the twos complement arithmetic and the ones complement arithmetic. They're both the same, and that's what makes the twos complement arithmetic preferred over the other.